often it can be quite difficult to visualize what curves are like in 3 dimensions. So we very commonly use a level, what's known as level curves. And the basic idea here is I have some function in two variables, x and y, that equals some other variable, perhaps z. So rather than trying to plot it in terms of z being equal to f of xy, rather than that we say it's equal to k, where k is some real number that's in the range of f. And this is the same idea as a contour map. Because think of it this way: if I have some three-dimensional object that looks, perhaps like this, it's got some curvature to it. Of course, that's kind of funky, but anyway. So this is some type of three-dimensional object. If I take a look at this when f of xy equals k for some specific value of k, really what I'm doing is I'm taking a slice of it. And then if I look down at it, there's some type of circular object, so I'm going to have perhaps concentric circles, or this may be elliptical. But what I'm going to see when I look down is maybe an ellipse that looks like this, that would be at this point. And over here was a little bit higher, maybe my ellipse would be a little bit bigger, like this. So each of these rings would represent a specific value of this function. Now we can do that in Maple. Let's take a look at this wind chill thing again. Here's the wind chill graph. And if I simply, in Maple, tell it I want a contour plot, there's my contour plot. Now, there's not a lot of curvature, a lot of stuff going on here, so this contour plot is not necessarily all that incredibly exciting. But let's go ahead and do the same thing, only with a contour, a 3D contour plot. And now what I've got is my original graph. This looks very much, let me make this a little bit bigger. This looks very much like our original function, because it is. Only this time what we're seeing is those contour lines. See, those are the same contour lines that we have up there. I'm not rotated the same way. If I spin this thing around, and let me see one more time, that's pretty much very close to the way my contour plot was setting. So let's take a look at a function that's a little bit more interesting. Let's do a three-dimensional plot of this guy. See, now here, if I look at this, I have all kinds of curvature here. So the contour plot should be kind of interesting. And actually, it may make a little bit more sense what the plot actually is. So I'm just going to go ahead and do a regular contour plot of this. And let's try to compare this with the original function there. So let's see what's going on. I'm going to try to rotate this around to kind of match where I am in a contour plot. Here's the x-axis and the y-axis. And you can see already that there's actually some contours in here, and it kind of matches what's going on here. So what's happening is the closer that these lines are together, the steeper the function is. So if I turn this on its side, we can see that we're heading down. So that's why these lines are pretty close together. We're actually looking at this side of this curve there. And on the bottom, we think of this as being a hole of the negative z-axis. That's red here. And I'm seeing also these bumps on top. That's actually higher, like a mountain ridge. That's coming up as yellow here. Now, in Maple, I can also do a 3D contour plot, like I did a minute ago with the wind chill. When I do that, I get the exact same color set up as this contour plot, but it's in 3 dimensions. So if I spin it, well, let's spin it around this way, then back down. If I look directly down on it, this is that contour plot. One's a little bit bigger and a slightly different angle. I could spin it a little bit more. Oh, it doesn't really matter. You get the idea. These two are actually identical. But the nice part about the 3D contour plot is, again, I can spin it up 3D. Now, remember I said earlier about each of these contour lines representing the value of the function at or of a specific value? That's what these lines are right here. These lines are where this function is equal to this specific value, all the way across the function in the domain that I actually graphed it.